Here are some practice problems for the differentiation rules we've learned so far. You might want to try these on your own before we solve them together. First one up is find the derivative of sine x times x squared. Here we have two functions multiplied together, the sine x and the x squared. When we multiply two functions, we use the product rule. F times g prime. Our f prime of x is going to start by taking the derivative of sine x, the first of those two functions multiplied together. And when we do that, we get cosine x. I've left it in parentheses just because the original one's in parentheses. So that sine x turns into a cosine x when we take its derivative. Then we multiply by the second function, x squared. You notice x squared does not have its derivative taken. Just the first one does. And then we add another term where we're going to reverse that process. This time we leave the sine x as it is, and we multiply by the derivative of the x squared, which we know from the power rule is 2x. Putting all that together, we have cosine x times x squared plus sine x times 2x. In this problem, the variable is named s instead of x. Don't let that throw you. F of s equals 1/2 times this expression, s to the fourth plus 7, which is all squared. See that? Now, we've got a power rule that tells us how to find the derivative of a variable that's squared or cubed or raised to the third power, but we don't have any rule yet that tells us how to do the same thing for a whole expression in parentheses that's squared. So don't make the mistake of just pulling the 2 down in front and making that a 1. We will get to a process for how to do that when we get to the chain rule, but right now we don't know how to do that. So the only way we have to deal with this squared business is to actually multiply it out. We have two copies of s to the fourth plus 7, because that's what it means to square something. And now it's clear that we have another product rule situation. I've got this times this. You might say, hey, wait a minute, Dave, what about the 1/2 there? Well, the 1/2 is also multiplied, but I don't have to use the product rule on it because it's just a constant. And as such, it can just come along for the ride. We don't have to do anything special for it. So the product rule says that I'm going to have to take the derivative of the first times the second, and so on. So let's do that. If I start with this first piece that I've underlined, the 1/2 comes along, and then I take the derivative of everything in parentheses there. So let's do that carefully. The s to the fourth, according to the power rule, becomes 4s cubed. That's that right there. What about the 7? Where's the 7 go? Well, the derivative of a constant is just 0. That's a special case of the power rule, but it's best just to remember that the derivative of constants that are added on, as opposed to multiplied, are 0. Notice that that does not apply to the 1/2 because the 1/2 is not being added, it's being multiplied times all this stuff. So now we've got the first piece. It gets multiplied by the second of these two factors, the second function that's being multiplied. So the derivative of the first times the second, and then we add, and now we're going to reverse that process. We're going to differentiate the second piece and multiply it by the first. Of course, there's an awful lot of similarity because these are actually the same two functions in this case. So you won't be too surprised to see something that looks like this. The 1/2 comes along again for the ride. This time, we don't differentiate the first one. We do differentiate the second one. And it's the same derivative, of course, 4s cubed, and the derivative of 7 is still 0. So we could simplify all that, but for the purposes of learning these rules, we're not going to dwell on simplification. We're just going to forge on to the next problem. Here we have x to the fourth times a cubed. I have to pay attention to what the function actually is. This is a function of x. So what the heck is this a? See that? There's an a in there. Somebody put an a in my function. In fact, they put a times a times a, otherwise known as a cubed. Why would they do that? I don't know. We'll never find out. But the point is that this variable x is the variable that the function cares about, and any other letters we might see in there, like pi or w or anything that's not x, is just a constant. That means it's some number that someone may choose to stick in there later, but for now we have to just leave it with a name rather than a number. The point is, after all that philosophizing, that even though it looks like in this case we might want to use the product rule because we have two things multiplied, that would ordinarily be the case, but this a cubed is not a function, or at least it's not an interesting function. It's just a constant. And when we find the derivative of a constant times a function, we just move the constant outside and take the derivative of the function. So that's a very long-winded way to say we can ignore the a cubed because it's a constant. So we find the derivative just using the power rule. The exponent 4 comes down front, we reduce it 1 to x to the third, and the a cubed, since it's just a constant, just comes along for the ride. It would be a different problem if the a cubed were x cubed. If it's x to the fourth x cubed, we could of course just write it as x to the seventh and immediately use the power rule on it, but let's play the game. So it's different now because x cubed is not a constant, it's a function. So in this case we get, using the product rule on x to the fourth, we get 4x cubed, and that gets multiplied by the x cubed, plus x to the fourth undifferentiated times the derivative of x cubed, which is 3x squared. You'll notice that you can combine terms to get 7x to the sixth, which is the same thing we'd get if we combined x to the fourth, x to the third into x to the seventh and then use the power rule. Here's another function we can look at. We've got two pieces separated by a minus sign. This should cause you, like Pavlov's dog, to salivate, because this means we can divide the problem into two pieces, treat them independently. That's because of our handy-dandy addition rule here. If we've got two functions separated by just a plus sign or minus sign, and we take the derivative, we can split it into two pieces. So let's take a look at the first piece, 2x times sine x. Well, that's a little bit more complicated there because I've got two functions of x multiplied by each other, and for that we need the, what is it? What's it called? Yes, that's right, the product rule, that one there. Alright, so the product rule says we take first function, differentiate it, 2x, derivative of 2x is 2, right? So far I have that. So I multiply that by sine x according to the product rule, the derivative of the first, the 2x times sine x, plus, now I'm going to leave the 2x alone and take the derivative of the second part, which is sine x, and the derivative of sine is cosine. So all this right here is the derivative of the first part of our function. Now we can put a minus sign and find the derivative of the second. Well, the derivative of cosine is just negative sine, so it looks like this. The minus sign here is the same as the minus sign here, and the derivative of cosine is negative sine. Of course, if we wanted to make this pretty, these two minus signs would cancel out and make a plus sign.